Research Center for Quantum Physics, National Research and Innovation Agency of Indonesia. And today I'm serving as a moderator for this colloquium. I would like to inform you that we usually organize our quantum physics colloquium 2 times every month. So we invite speakers from our research center and also guest speakers from other institutions. And for today, it's my pleasure to introduce our speaker, Dr. Gyu Jang from Kyung University, Korea. Thank you very much for being with us today. And you already share your screen, so it looks okay. Today, Dr. Gyu Jang will talk about van der Waals heavy-fermion cerium silicon iodide dynamical mean field theory study. And this talk will give an introduction about dynamical mean field theory calculations, which is commonly used to simulate the physical properties of strongly correlated electron systems. He will also discuss one of the application in the field, and in this case is his work on van der Waals heavy-fermion cerium silicon iodide. And before we start, please allow me to briefly introduce our speaker. Dr. Gyu Jang obtained his PhD degree from Pohang University of Science and Technology, South Korea. He is now currently an assistant professor in the Department of Material Science and Engineering at Kyung University. Dr. Gyu Jang is a close collaborator and colleague of mine, and in my opinion, he's one of the experts in the DFT and DMFT calculations, especially when dealing with strongly correlated electron systems. And so with that, I guess we can start. Dr. Jang, as I mentioned before to you, you will have 50 to 60 minutes for your presentation, which will be followed by an open Q&A session of about 20 to 30 minutes. And for the audience, if you have any questions during the presentation, please post your question in the chat box, and I will pass it along to Dr. Jang later on. So without further ado, an introduction, Dr. Gyu Jang, the floor is yours. You can start. Thank you.
Okay, thank you. So first of all, I'd like to thank my friend Dr. Lesta for the invitation and the nice introduction. So today I'm Gyu Jang from Kyung University, and today I'm gonna talk about the 2D van der Waals heavy-fermion material cerium silicon iodine, which is the first realization of heavy-fermion physics in the 2D limit. And this study is based on the first principle calculation, especially with the density functional theory combined with the dynamical mean field theory. So before going on, I just want to briefly introduce the Kondo effect and the heavy-fermion physics. So let's start from the textbook example. So in 1930, people found that the resistivity minimum in many metal systems at low temperature. So when you see this figure at the left side, you can see that this is the temperature and this axis indicates the resistivity. And as you can see, by lowering the temperature, we can see some minimum behavior and resistivity going up below certain temperature scale. But at that time, people couldn't understand the origin of this behavior. But after 30 years later, people realized that the tiny amount of magnetic impurity in the metal induced this kind of resistivity minimum behavior. And finally, the Jun Kondo, the Japanese physicist, provide the first theoretical description for this kind of resistivity minimum behavior in many metallic systems with magnetic impurity. So at high temperature, this magnetic moment just remain as alone and do not interact with the conduction electron. So above the Kondo temperature, it just remains as a magnetic moment. However, when we decrease the temperature and below the Kondo temperature scale, these magnetic moments start to interact with the conduction electron. So below the Kondo temperature scale, it starts to screen by the conduction electron, and this kind of Kondo cloud can be acted as some kind of scattering source, so that the resistivity increase at very low temperature. So this is what we learned from the solid state textbook. So then let's move on to the Kondo lattice problem. So what if this kind of magnetic moment form the lattice like this? So this kind of so the difference between the Kondo lattice and Kondo impurity system can be realized in this kind of cerium lanthanum copper 6 material. So by tuning the contents of the cerium atom in this system, we can tune the system from the Kondo impurity to Kondo lattice model. So lanthanum does not have any F electron in the F shell, so it does not have any local magnetic moment. However, the cerium atom has one electron. It's in its very localized 4f orbital. So the cerium atom can be act as some kind of magnetic impurity. So if the x equals 0, which means that if there is no cerium atom in this compound, there is no magnetic impurity, so that the resistivity exhibits just a normal metallic behavior. So x-axis indicates the temperature, and y-axis is resistivity, and x-axis is in the log scale. But if we put some cerium atom in this system, then as we already discussed in the previous slide, the cerium atom can be acted as a magnetic impurity, so that we can also observe this kind of resistivity minimum behavior at low temperature. So even at x equals 0.5, we can still see some kind of resistivity minimum, and below this temperature scale, the resistivity is going up. But above this x equals 0.5, so at x equals 0.73, now we can see some kind of hump here at lower temperature. So the resistivity is going up and going down again. And when we increase the content of cerium atom more and more, now we can clearly see this kind of resistivity maximum behavior below this minimum behavior originating from the Kondo effect. And finally, with the x equals 1, which means the cerium copper 6 pure compound, now we can clearly see this kind of resistivity maximum behavior. So that below this temperature scale, usually we call it the resistivity maximum point as a coherent temperature. So below this temperature scale, the system recover its coherence, and the resistivity is going down again. So what happened in this kind of Kondo lattice system? So at high temperature, above the Kondo temperature, as I already told you in the Kondo impurity system, this kind of magnetic moment just remains as a magnetic moment at each atomic site. And usually the 4f orbital is very localized, so that the f electron at each atomic site cannot see each other, so that it cannot form any band structure So at high temperature, only the conduction electron participate the Fermi surface formation, and the f electron does not participate into this kind of Fermi surface formation. But when we decrease the temperature, so below the Kondo temperature scale, the conduction electrons start to interact with this kind of magnetic moment at each side, and it starts to form Kondo cloud, which is the screening of the magnetic moment by the conduction electron. And below a certain point, these Kondo cloud now can see each other, so that it can start to participate the Fermi surface. So at very low temperature, we have this kind of band structure. So at the Fermi level, we have very flat band, which has very heavy mass. That's why we call it this kind of material as a heavy-fermion system. So typically, heavy-fermion exhibit the the heavy mass, which usually 100 to 1,000 times larger than the free electron mass. And another important feature is that because of the hybridization between the conduction and F electron, we now have this kind of hybridization gap feature near the Fermi energy. And due to the participation of F electron into the Fermi surface, now we have large Fermi surface at low temperature compared to the high temperature. So this is just brief introduction for the Kondo effect and the heavy-fermion material. But this kind of feature, I mean, the temperature dependence of the electron evolution cannot be understood in terms of single particle electron. So usually density functional theory, which is most popular computational method for the electronic structure, is not proper to describe this kind of heavy-fermion system. First, density functional theory can only describe the zero Kelvin limit. And second, although there is some correlation effect is included in the density functional theory, it is still based on the effective single particle picture. So it cannot properly describe the electron-electron correlation. So the heavy-fermion system usually occurs in the lanthanide or actinide material, which has very localized 4f and 5f orbital. And the electron in this kind of very localized 4f or 5f orbital feel very strong electron-electron Coulomb interaction between them. So now it is very important to describe this kind of Coulomb interaction to understand the heavy-fermion system or the motor insulator, something like that. So when we see the non-interacting electron system, there is no scattering between them, and we can just, this is the energy and this is the momentum. We can get a just energy momentum relation, which is just band structure obtained from DFT calculation, and it exhibits just the delta P-like structure. However, when we have the electron-electron interaction, which is actually realistic system, in the realistic system, now we have very different picture compared to the non-interacting electron system. First of all, when we see the band structure near the variable, still we can clearly see very sharp peak at the variable. But when we move away from the variable, this kind of quasi-particle peak reduce. And another point is that the spectral weight is transferred to the high energy feature, so that we can see that this kind of additional Hubbard band picture. So to describe this kind of realistic picture, and this is what we observe in the RPS or photo emission spectrum. So we need to deal with these kind of electron-electron interaction properly, so that we can easily understand this kind of picture within the Green's function terminology. So this is the Green's function in a function of the momentum and the frequency or the energy. And here we have the EK, which is the non-interacting band dispersion. And then here we have the sigma, which is the electron self-energy due to the electron-electron Coulomb interaction. And as you can see, these kind of self-energy usually have the momentum dependence and also the frequency and energy dependence. And from this kind of Green's function, we can get a spectral function here. And when you see this kind of formula properly, then we can realize that the real part of self-energy induce the energy shift, because here we can clearly see that this kind of real part self-energy induce the energy shift, which is related to the band renormalization effect, which is usually observed in the correlated system. And another point is that the imaginary part of self-energy induce some kind of broadening effect, which is related to the lifetime of the electron. So now we have to include this kind of effect to describe the correlated system properly. So we can do this by using the dynamical mean field theory. Also, although it has still some kind of limitation. So this is the Hubbard model, which is the simplest model to describe the electron-electron correlation effect. So the first term just describe the hopping between two different sides, and second term describe the Coulomb interaction between two different spins at the same I side. So this is the simplest model, but we cannot solve this problem exactly except the 1D limit. So it is very difficult to solve the correlation effect properly. So the basic idea of dynamical mean field theory is that we just project this lattice problem into the endless impurity model, so that then we can solve the problem in certain limit. So this kind of mapping, I mean the local approximation by mapping the lattice problem into the impurity model, now we lose some information. I mean the K dependence of dependence, we cannot describe the K dependence, momentum dependence in this kind of approximation. but still we can properly describe the energy dependence of the self-energy effect. So if the momentum dependence of self-energy is not that large, then we can safely use the dynamical mean field theory. And usually most of strongly correlated system, on-site Coulomb interaction is important. So the momentum dependence usually is small. So we can safely use the dynamical mean field theory to treat many kinds of strongly correlated material. So in this kind of approximation, I mean the mapping from the lattice problem into the impurity model, we can say that the Green's function from the lattice is equal to the Green's function from the impurity model, and also the self-energy is same for these two problems. And another important point is that when we see this kind of Anderson impurity model, the Hamiltonian have three different terms. First is the best term, so it just describes the conduction electron. And another term is the impurity side. So it just describes the local magnetic moment and the Coulomb interaction between them. And this kind of impurity side and the best side connected by this kind of second term, which is the hybridization. So this hybridization allows to describe the charge fluctuation between the lattice side and the bed side. So depending on the time, the spin can be in the impurity side and another spin come from the bed side. And this kind of dynamical property, I mean, which related to the frequency can be described by this kind of hybridization term. So when we see this this formula, this is the hybridization function, which is related to the VK, which indicate the hybridization between the impurity side and the bed side, is the most important part of this dynamical mean field theory calculation. So this hybridization function have the frequency dependence, so that's the reason why we call dynamical mean field theory. So in this sense, we can get this kind of formula. So we can just say that the Green's function from the lattice side and the Green's function from the impurity side can be equal. So from this relation, we can self-constantly obtain the self-energy from the impurity dynamical mean field theory part, so that we can describe the electron-electron correlation effect properly. So first, we can just start from the initial guess for the self-energy, and by putting this self-energy, we can get a lattice Green's function. So from when you see this lattice Green's function, we have this kind of non-interacting band dispersion information here. So we can get this information either from the just model Hamiltonian or even from the density function theory. So if we can get this energy dispersion information from the density function theory. That's the density function theory combined with the dynamical mean field theory, which is DFT plus DMFT calculation. Then we can, using this relation, we can get a best Green's function, and by using the impurity solver, we can get a new impurity Green's function, and from this relation, we can get new self-energy for the system. And by using the self-constant loop, we can get a converged self-energy, which can describe the electron-electron correlation effect of the system. So now I just want to briefly show some good example, what DMFT can do for us. So first example is the correlated metallic system strontium vanadate. So in this system, the vanadium atom has one electron each d shell. So this is the density of state obtained from the density function theory calculation. And as you can see, it has octahedral symmetry. So D level split into T2G and EG level. And as you can see, EG is completely empty, and we have one electron in the T2 shell. Another important point is that within this DFT picture, we don't have any spectral weight of around -2 eV. But because of the localized d electron of vanadium atom, the electron in the d shell feel Coulomb interaction. So this red line is obtained from DFT plus DMFT calculation. So compared to this blue line, which is obtained from DFT calculation, the one important point is that the bandwidth is renormalized, so that the bandwidth obtained from DFT calculation is narrower than DFT bandwidth. And another point is that we have additional spectral weight at high energy, which is the Hubbard band. So around -2 eV, we have additional picture which is absent in the DFT calculation. So now I want to compare this DFT calculation and DFT calculation with the experimental result. So this is the result from the photoemission spectrum data. So this circle indicates the photoemission spectrum data, and this dotted line indicates the DFT calculation. So when you compare this photoemission spectrum and DFT calculation, DFT overestimates the bandwidth, and we don't have any, in the DFT calculation, we don't have any feature in around -2 eV, but in photoemission spectrum, we have some additional picture like this. But DFT cannot describe this kind of thing. But by using DFT plus DMFT calculation, now the bandwidth well agree with the experimental result, and also we can describe this kind of Hubbard band picture here. So this is the RPS data obtained from the experiment. So there is some kind of strong intensity here, and there is another intensity around -1.5 eV, which is very incoherent. So, but when you see this line structure, which is obtained from DFT calculation, DFT overestimate the bandwidth here, and also DFT cannot describe this kind of additional very incoherent feature here. But when we properly describe electron-electron correlation within DMFT limit, now we can describe this experimentally observed bandwidth here, and also we can describe very incoherent Hubbard band picture at around -1.5 eV. So to describe the correlated metallic system, we need dynamic mean field theory, because DFT we cannot describe band renormalization, and we cannot describe Hubbard band picture. And another example is that by using the dynamic mean field theory, we can describe successive or consecutive metal insulator transition. So this example is the nickel disulfide and selenide system. So nickel disulfide is the very famous multi-insulator. So here the antiferromagnetic insulator indicate the nickel disulfide case. But nickel diselenide is just a correlated metal, so it exhibits just paramagnetic metallic behavior. So by controlling the sulfur or selenium content, we can make some metal insulator transition. So this is the experimental observation. So at x equal 0.43, now still we can see some band dispersion at the variable, but above this point, we cannot see any spectral weight near the variable, which indicate the multi-insulating phase. But this kind of picture cannot be described by the density functional theory. But within DFT plus DMFT calculation, we successfully describe the successive metal insulator transition behavior within this material. And as you can see, we can also describe the band renormalization even in this kind of correlated metallic system. Finally, for the heavy-fermion system, definitely we need dynamic mean field theory calculation, because DFT calculation cannot describe the temperature dependence evolution. So this is the very first example of the dynamic mean field theory calculation applied to the very famous heavy-fermion system, cerium-iridium indium-5. So at very low temperature, we can clearly see there is a very flat band at the variable. However, at very high temperature, we cannot see any flat band feature at the variable, and we can only observe a very dispersive conduction band. So when we zoom in this RG direction, at low temperature, due to the hybridization between the F electron and conduction electron, we can clearly see the hybridization gap feature here. As I already discussed in the very first slide. At high temperature, the F electron does not participate in the Fermi surface formation, so we cannot see this kind of hybridization gap feature and flat band feature at the variable. So DMFT calculation can describe this temperature dependence of band evolution. So actually, this image, how can I say? So this is also obtained from the dynamic mean field theory calculation. So depending on the temperature, at high temperature, we only have this kind of conduction electron, but low temperature, we have a very flat band at different level. And by using dynamic mean field theory calculation, we also can explain this kind of a relativity maximum behavior, which observed in the experiment. So this is my brief introduction for the dynamic mean field theory and what dynamic mean field theory can do for us. So let's move on to my research topic. So today, as I already mentioned, I'm gonna discuss about the intrinsic 2D van der Waals heavy-fermion system. So I think since the discovery of the superconductivity in the magic angle graphene and the magnetic ordering in the 2D limit, in the 2D van der Waals material, has stimulated the renaissance in the field of 2D van der Waals material, I think. So I'm the heavy-fermion guy. So when I see this kind of discovery of 2D magnetic material, it motivates me to discover the intrinsic 2D van der Waals heavy-fermion system. So now we have very many types of 2D van der Waals material showing various physical properties such as ferromagnetic or the antiferromagnetic ordering or ferroelectricity. And one of the missing components in the 2D van der Waals material is intrinsic heavy-fermion system. So if one can realize the heavy-fermion physics in 2D limit, then we can get another building block to study the emergent phenomena in the van der Waals heterostructure or the van der Waals in the 2D limit by applying the external gating or by applying the strain or the surface topic, something like that. So that's my the motivation. So although I already discussed some background of the heavy-fermion, I briefly mentioned about another energy scale which is important in this kind of heavy-fermion system. So actually, as I already told you, this kind of heavy-fermion behavior usually observed in the lanthanide system, which has very localized orbital. So in this 4f electron system or 5f electron system, there is two important energy scale. One is the RK-KY interaction, which induces the magnetic ordering, long-range magnetic ordering, and another is the Kondo effect, which I already briefly introduced you in the very beginning of my presentation. So if the RK-KY interaction dominates over the Kondo temperature scale, then the material exhibits the long-range magnetic ordering, usually the antiferromagnetic ordering at low temperature. And as I told you, in this case, the F electron does not participate in the Fermi surface formation, so it has a small Fermi surface. However, if the Kondo temperature scale dominates over the RK-KY interaction, then the ground state will be the paramagnetic Kondo resonance state, and this kind of F electron can participate into the Fermi surface formation. So now we have very large Fermi surface. So, but this kind of ground state can be easily tuned by the external perturbation, since this kind of two energy scale is very small. So usually in the heavy-fermion, we can easily tune the ground state by applying the pressure or the magnetic field. So the cerium cobalt indium 5 and cerium rhodium indium 5 and cerium iridium indium 5 is the most famous the heavy-fermion family. Actually, this is the bulk system, 3D bulk system. And cerium cobalt indium 5, it has paramagnetic ground state, paramagnetic heavy-fermion ground state, and at low temperature, it exhibits superconductivity. However, when we change the cobalt atom into rhodium atom, then the ground state is the antiferromagnetic ordering. And then when we apply the pressure, so above only 0.5 gigapascal, the ground state easily changed from antiferromagnetic ground state to paramagnetic heavy-fermion state. And at low temperature, it also exhibits the superconductivity. And by applying the external magnetic field, we can also tune the ground state property, because this kind of two energy scale is too small, so it can be sensibly tuned by the external perturbation. So if one can realize this kind of heavy-fermion physics in the 2D limit, then we can tune this ground state by another method, like the gating or the strain or surface hopping, like this. So, but actually there has been some study to study this kind of heavy-fermion behavior in the 2D limit. So actually Japanese group, they did a lot of things in this kind of field. So by epitaxially growth of the cerium indium-3 and lanthanum indium-3 alternative layer, they study the heavy-fermion behavior in the 2D limit. So by reducing the cerium indium-3 layer, which sandwiched by the lanthanum indium-3 layer, they find some kind of behavior can be changed within the very thin limit. So in this case, they found some different scaling behavior compared to the 3D part, but this is not an exact 2D limit. And recently, people suggest that this kind of heterostructure, 1T tantalum disulfide and 1H tantalum disulfide, can also exhibit some heavy-fermion behavior within the 2D limit. And actually, I missed some part in the introduction. So, but anyway, so now I want to emphasize that the two important ingredients to make the heavy-fermion behavior is that first one is the local magnetic moment, and second one is the dispersive conduction electron to screen the magnetic moment. So that's the two important ingredients in the heavy-fermion system. So in this heterostructure, 1T tantalum disulfide, actually it is well-known motor insulator. So in this 1T tantalum disulfide, we have very localized magnetic moment in this layer. But 1H tantalum disulfide is well-known just metallic system, so it has conduction electron at different level. So they suggest that by interlayer Kondo coupling, this material can exhibit the heavy-fermion behavior. But actually, this is there has been some controversy in this heterostructure and the heavy-fermion system. And actually, I do not believe this is the heavy-fermion behavior, but I just think this is just a doped motor insulator. So recent theoretical study suggests that this is not a heavy-fermion behavior, but the doped motor insulator. And another example is that also the twisted graphene also exhibit some kind of heavy-fermion behavior. But it is also tricky because the very sophisticated preparation is needed to induce the flat band at different level and to screen the local magnetic moment. But recently, people actually are interested in this kind of Moiré system to realize the heavy-fermion behavior within the 2D limit. But actually, it is not an intrinsic heavy-fermion system, but extrinsic heavy-fermion system. So it is not easy to control their properties within the experiment. So that's my motivation. So that's why I'm trying to discover the 2D heavy-fermion system within the van der Waals material. So my starting point is the database. So these days the machine learning study or the big data study is popular. So now we have very many material database. So actually in 2018, the Mazzari group, they proposed more than 1,000 easily exfoliable compound from these already experimentally known compound. So they, by using the calculation, they suggest this kind of 1,000 exfoliable compound. So that's my starting point. So from the experimentally known compound, I was trying to discover the system which can exhibit the heavy-fermion system. So, but as I told you, so to get the heavy-fermion physics, we need two ingredients. First one is the very localized orbital. which usually the 4f orbital, and another one is the conduction electron. So although they suggest these more than 1,000 compound, but actually I only consider 32 lanthanide compound, because the lanthanide compound actually they have 4f electron, 4f orbital, so that they can have the local magnetic moment. So we can reduce the easily exclude another material. So I just focused on these 32 lanthanide material among them. And as I told you, to get the heavy-fermion physics, we need localized f electron and conduction band at the level. So to confirm the conduction band at the level, I just ran the open core DFT calculation, which hide the f electron into the core level, and we can get another band. We can exclude the f electron, and we can only focus on the another conduction electron. So to screen for the first screening, we just run the open core DFT calculation. So this is the open core calculation result. So x-axis indicate the 32 lanthanide material, and y-axis indicate the density of state at the level based on open core DFT calculation. So if there is some density of state, that means there is another conduction electron originating from the non-f orbital. And if there is no conduction electron, then we don't have any chance to make the heavy-fermion physics. So this one we can safely ignore, because there is no conduction electron to screen the magnetic moment. And also we can ignore the lanthanum compound, because lanthanum atom, they do not have any local magnetic moment in their shell. And we can also ignore this lutetium compound, because lutetium has completely filled 4f electrons, so that it cannot induce the local magnetic moment. Then we only have 4 remaining compounds, but still we can classify these 4 compounds into 2 classes. The first one is the cerium silicon iodine. So in the cerium silicon iodine, the conduction band is coming from the ligand atom orbital. However, this yellow one, the conduction band is coming from the lanthanum d orbital system. But actually, based on this kind of classification, we can easily believe that this cerium silicon iodine, which has the conduction band from the ligand atom, is good candidate for the heavy-fermion system. I will explain that explain it in this slide. So actually, the gamma cerium, alpha cerium, actually they have same FCC structure. However, only the difference between them is the volume. So there is some volume collapsing under the pressure, about 15%. However, the gamma cerium exhibit the Curie-Weiss law, which indicate the existence of the local magnetic moment. However, on the other hand, in the alpha cerium case, it has smaller volume, and it exhibits Pauli-Para behavior, which indicate that the conduction electron screen the f electron, so that it exhibits some kind of heavy-fermion behavior. So what's the difference between them? I mean, the difference between the gamma cerium and alpha cerium is just the volume. So depending on the volume, the alpha phase, this is the result obtained from DFT+DMFT calculation. The alpha phase, we can clearly see the flat band at the level, which indicate the heavy-fermion behavior. However, for the gamma phase, we cannot clearly see the flat band at the level. So to screen the f electron with the lanthanum d orbital, we need smaller volume, which indicate the short distance between them. So for the alpha cerium case, the distance between 2 cerium sites is close, so that the Kondo cloud can see each other, so that they can easily form the flat band at the level and participate the Fermi surface formation. However, for the gamma cerium, although the Kondo cloud can be formed, but still they cannot see each other, so they cannot participate the Fermi surface formation. That's the important point. So to screen the f orbital with the lanthanum d orbital, the distance between them is the key point. However, so this is the distance between the lanthanum atom for the gamma cerium case and another candidate for the 2D heavy-fermion case. But as I told you, gamma cerium is very weakly heavy-fermion system, and the distance between them is 3.65. But for other this candidate, the distance between the lanthanum atom is larger than the gamma cerium case, which indicate that this three candidate is not good for the heavy-fermion realization. And for the comparison, actually here we have the ytterbium I2 and thulium I2 here. Although in this database study, I'm sorry. So in this study, actually they did not propose the cerium iodine as an exfoliable compound, but actually for the comparison, I just put the cerium iodine here. And cerium iodine has 3.87 angstrom distance between the cerium atom. And then by using the DFT+DMFT calculation, we clearly found that there is no Kondo peak at the variable. And this is the constant with the experimental result. And it is well known that the cerium iodine 2 has a magnetic antiferromagnetic ground state at low temperature. So that we can easily exclude the other compound where the conduction electron coming from the lanthanum d orbital, so that we conclude that the cerium silicon iodine, where the conduction electron is coming from the ligand atom, is a good candidate for the realization of the heavy-fermion physics. So the cerium silicon iodine actually was firstly reported in 1998. And since then, actually, there has been no study on this compound. Actually, this when you see this kind of structure figure, the cerium silicon iodine van der Waals layer consists of this silicon layer, which is silicon analog of the graphene. So here we have some graphene-like silicon layer here, and it is surrounded by the cerium cage, which so here the green color indicates the cerium atom. And finally, there is some outer iodine layer here. So van der Waals gap is defined with this kind of iodine. And actually, this material is classified as a gentle Klein phase, which is characterized by the intermediate metallic and ionic bonding. So in this picture, so this additional electron is distributed over the cation. So in this case, so this additional electron is just distributed over in this cerium cage. So in this, so this is the important for the screening of the cerium local magnetic moment. So to understand its electron properties, first we perform the open core DFT calculation, which hide the F electron in the core level. So now this is the open core DFT calculation for the cerium silicon iodine, and actually the banded dispersion at around -2 eV actually is quite similar with the silicon layer, while the Dirac point in the silicon is located at the Federal level. But in this cerium silicon iodine, the Dirac point is located at -2 electron volt, which indicate the charge transfer to the silicon layer. So this means the charge so cerium atom give the electron to the silicon layer. So in this picture, we can expect the band crossing at the variable actually is coming from the silicon PX and PY antibonding state. However, when you check the density of partial density of state here, actually density of state coming from the silicon layer is quite small. And the most of contribution at the variable is coming from the interstitial region, which is indicated by this yellow line. So it means the near the variable, the electron is mostly coming from the interstitial side, which well agree with the gentle phase properties. So this is the electron density distribution figure. So here the yellow, the green indicate the larger electron density. And as you can see, within the cerium cage, the electron just floating all around the cerium cage. So this feature well agree with the Jinterklein nature. And this floating electron in this within the cerium cage nearby the silicon layer can be the ingredient for the heavy-fermion state, which can screen the F electron at the cerium atom. So to investigate the hybridization between the cerium-4F electron, conduction electron, and the cerium-4F electron properly, we perform the DFT+DMFT calculation. And here we do not consider the ground state, whether it is antiferromagnetic or the paramagnetic. So here we just consider the paramagnetic state to understand its Kondo scale. So left panel shows the spectral function of the bulk cerium silicon, and right panel show the spectral function for the monolayer cerium silicon iodine. And actually, two are actually pretty much same. And we can clearly see that there is some Kondo resonance peak at the level, indicating the substantial hybridization between the cerium-4F electron and the conduction electron. So, actually, this figure B indicate the temperature dependence of evolution of the Kondo peak at the level. So for the bulk and monolayer. And as you can see, even the temperature dependence of evolution of the Kondo resonance peak also does not change upon the exfoliation. So therefore, we can conclude that the cerium silicon iodine monolayer can provide an ideal platform for the for exploring the heavy-fermion physics in the 2D monolayer limit. And next, we investigate the external perturbation effect on the Kondo resonance state of the cerium silicon monolayer. So now we can get the heavy-fermion physics in the 2D layer. Unlike the 3D bulk case, we can tune the ground state by using the strain or the surface doping. So this figure shows the electronic structure of the cerium silicon monolayer with the biaxial strain from -4% to 4%. So upon compressive strain, the volume of cerium cage surrounding the silicon layer decreases. Therefore, one can easily expect the stronger F and conduction hybridization under the compressive strain due to the enhanced conduction electron density within this cerium cage. So when you see the Kondo resonance peak in this figure, as you can see, within the compressive strain, the Kondo resonance peak is quite enhanced compared to the just pristine cerium silicon iodine. And when we apply the tensile strain, the Kondo resonance peak decreases. And actually, this is the temperature dependence of evolution of the Kondo resonance peak at the Fermi level. And we can actually roughly expect the Kondo temperature scale from the logarithmic T dependence of this behavior. So within the pristine monolayer, the Kondo temperature scale is about 120 Kelvin. But when you apply the tensile strain, the Kondo temperature increase up to 200 Kelvin. So that the tensile with the tensile strain, we can easily tune the ground state. And another point is that when we see the hybridization gap feature here, the hybridization gap here is small and hybridization gap here is larger. So this is due to the different orbital character of these two different conduction bands. So this is the fat band plot obtained from the DFT calculation. So this conduction band is mainly coming from the cerium D orbital, and this band is mostly coming from the silicon atom. And as I told you, with the cerium D orbital, it is not easy to fully screen the F orbital, so that the D orbital just make very small hybridization gap here. But with this cerium dispersive conduction band, we can get a very large some hybridization gap feature. So we can also observe this kind of orbital dependent behavior here. And another point is that at high energy point, this is the empty 7-half orbital case. So here we can clearly see that the hybridization between the 7-half case also enhanced, so that we can clearly see the kink behavior here. And another point is that now we can tune the ground state by using the surface doping. So here we have two different cerium atoms within the monolayer. So here upper cerium, we have lower cerium here. And by tuning the number of electron outer iodine layer, we just mimic the surface doping case. So I think we have 10 minutes, so I think maybe I have to hurry up. So when we change the number of electron at the outer iodine layer, but the total number of F electron in the upper cerium and lower cerium does not change that much. However, depending on the cerium side, the Kondo resonance peak at different level behave differently. So upper cerium atom, when we change the when we dope some electron or introduce some hole, the Kondo resonance peak significantly change. So by introducing the hole doping, we found that the Kondo resonance peak enhanced significantly compared to the pristine case. And by introducing the electron, the Kondo resonance peak at different levels slightly decreases. But however, the Kondo resonance peak from the lower cerium atom does not change that much for the surface doping. So here we found that the surface hole doping can enhance the Kondo resonance peak, or the tellurium substitution would be also effective to enhance the Kondo resonance peak. However, we found that the silicon substitution is not that effective. So maybe, so actually to understand this figure I think I need to spend some time. So I just want to move on to another page. So just keep in mind that we can easily control the Kondo resonance peak by the surface doping here. So the remaining important question is that what is the ground state of this material, and how sensitive the ground state of cerium silicon iodine can be changed by the strain or the surface doping I discussed in the previous page. Actually, in principle, one can predict the ground state of this heavy-fermion material by comparing the Kondo energy scale and RK-KY interaction scale. But actually, it is not easy to calculate those energy scale properly with the DFT or even with the DMFT calculation due to the very small energy scale. So to answer this question, we have constructed the phase diagram by calculating the inverse tensor of state at the x-axis and the inverse quasi-particle lifetime, which is related to the scattering rate in the y-axis. And we just compare with the well-known cerium-based material. So here we just consider the paramagnetic state for every compound, regardless of their ground state, to construct this phase diagram. So here we just first I just put some well-known cerium-based material, and the circle indicate the representative paramagnetic heavy-fermion system, while this diamond symbol indicate the material showing the magnetic ordered state at low temperature. And here for the barrier comparison, we renormalize two physical quantity with those of cerium cobalt indium 5, which is located close species of quantum critical point. And actually, interestingly, these well-known cerium-based materials are well classified with these two physical quantity, the density of state and the inverse quantum particle lifetime. So typical paramagnetic heavy-fermion system are located below the cerium cobalt indium 5 here, and the magnetic ordered system are located above the cerium cobalt indium 5 point. And although these three compounds show antiparamagnetic ground state, but they have been intensively studied as an antiparamagnetic heavy-fermion system since their ground state can be easily tuned into the paramagnetic heavy-fermion state by external perturbation. So the cerium indium 3, which is the B, when by applying the 2 gigapascal, it turns into the paramagnetic heavy-fermion system and exhibit the superconductivity. And for the C, which is the cerium copper 2 germanium 2, we can also easily tune the ground state to the paramagnetic state by applying the pressure. So this can be these materials have been studied intensively as an antiparamagnetic heavy-fermion system. And we found that the cerium silicon iodine monolayer is above the cerium cobalt indium 5 point, indicating magnetically ordered phase. And actually, this prediction well agrees with the recent experimental result on the bulk cerium silicon iodine. So in this study, they found that the cerium silicon iodine has a complicated magnetic ordering at low temperature. However, the cerium silicon iodine is located near the cerium copper 2 silicon 2 and the cerium indium 3, so that we can expect the ground state of cerium silicon iodine can be easily tuned by external perturbation. So here we indicate the cerium silicon iodine monolayer with the surface doping and the strain. So with the -4% strain, I mean the 4% of compressive strain, it is located right below the cerium cobalt indium 5, indicating a possible quantum phase transition to paramagnetic heavy-fermion state from the antiparamagnetic state. And with the 0.1 hole surface hole doping, it moves further below the cerium cobalt indium 5, and it is located near the well-known paramagnetic heavy-fermion material cerium iridium indium 5 and the cerium copper 2 silicon 2. Therefore, the cerium silicon iodine monolayer is promising 2D Van der Waals heavy-fermion candidate, and its ground state can be easily tuned by the external perturbation. So by introducing the surface doping, surface hole doping, and the strain, we can find some quantum critical point, or I believe we can even study some unconventional superconductivity. So I think this new material provides the new way to study this kind of interesting physics. And I just want to let you know that after my study, actually experimentally successfully synthesized this material after since the 1998, and they actually observed the heavy-fermion behavior, and this study actually is published in the Nature. So when you compare these RPS data with my dynamical mean field theory calculation data, they well agree with each other. And here, this is actually the spin-orbit coupling sideband here. Although within this picture, it is not that clear, but in this picture, we have very incoherent spectral rate here. And it gives this kind of kink behavior here, which well agree with these experimental data. So I'm really happy to have this Nature paper, because that means that my prediction is successful, and now we can study this kind of heavy-fermion behavior within the 2D Van der Waals limit. So let me summarize my study. So we investigated 2D Van der Waals heavy-fermion system from the experimentally non-compound, and cerium silicon iodine is the most promising candidate. And we found that the compressive strain or surface hole doping can enhance the Kondo resonance state. So I believe the cerium silicon iodine can provide a new degree of freedom to study quantum critical point and unconventional superconductivity and emergent phenomena in the Van der Waals heterostructure. So that's all for my slide. And I just want to thank my collaborator. Actually, this work was done with the Dr. Jian-Shin Ju in the Los Alamos National Laboratory in United States and Professor Ji-Yoon Shim in the postdoc in Korea. And finally, I just want to brief advertisement on the ICAMD conference. Actually, this conference is International Conference on Advanced Material and Device. So this will be held in Busan in Korea. So Busan is the second largest city in South Korea. So Busan is surrounded by the ocean and mountain, and it is very beautiful city. And in this ICAMD conference, we cover a variety of topics, including the quantum information and the nano material and the oxide heterostructure and the neuromorphic device. So if we are interested in, please keep in mind this important date for the abstract subscription and registration. So I hope we can meet in person in this great conference in this December. So thanks for the, thank you very much for your attention.
Okay, hello. Okay, thank you, Dr. Jang, for your interesting presentation. Actually, this talk really gives us valuable insights about what PMFT, DFT, and DMFT is, what it can do, and also how to apply it in the case of strongly correlated electron systems. It is also interesting to hear about the heavy fermion case in the two-dimensional limit, which is opened by the discovery of your prediction initially and experimental confirmation of the heavy fermion in the two-dimensional limit in the case of cerium silicon iodide. So I think this talk will be especially valuable and inspiring for us. Now we have around 30 minutes for our Q&A session. To all participants, if you have questions, you can either post your question in the Zoom chat or raise your hand if you would like to ask the question directly to the speakers. Okay, so we have two questions already.
Yeah, we have.
And so which one?
I'm reading the question from the chat. Maybe okay, so I can just answer from the top, I think. So first question is the regarding the two energy scale, the RKKY interaction and the Kondo temperature scale. So what happens if the RKKY temperature scale and Kondo temperature scale is equal? So that I will, so actually if the two temperature scale is equal, then that means we can get some quantum critical point. So if, as I told you before, so if the RKKY interaction is larger, is dominant over the Kondo temperature scale, we can get a magnetic ground state. And if the Kondo temperature scale dominate over the RKKY interaction, we can get a heavy fermion ground state. But between them, there is some kind of crossover. So that's the quantum phase transition. So if the two energy scale is exactly the same, we can get a quantum critical point. So like this. So in this nearby the quantum critical point, we can usually observe the strange metallic behavior, which does not follow the ferromagnetic behavior like the T-scale resistivity behavior, something like that. And near this quantum critical point, we can we can find some unconventional superconductivity, and it is quite similar with the cuprate-based superconductivity, something like that. So if the two energy scale is same, then we can get a quantum critical point, and usually we can get, then at the quantum critical point, we can get a strange metallic behavior, and even sometimes we can get a superconductivity behavior. So that's my answer for the first
we have another question also.
And
the second one about Janus heterostructures from Dr. Ada Smajic. Can you scroll it down?
Yeah, so for the second question, so actually recently, so actually tungsten or moly case, actually within just a normal case, we don't have any local magnetic moment in this material. So we cannot get the heavy-fermion behavior, but recently people are trying to twist them within the bilayer limit. So by applying the twisting, we can get some moire pattern within this kind of molybdite selenide or molybdite telluride case. And if there is some kind of moire potential, some electron can be localized in some site, and on another side they can act as conduction electron. So people theoretically suggest that this kind of moire molybdite telluride material can induce the heavy-fermion-like behavior. Yeah, so I'm not sure it is confirmed by the experiment or not, but anyways, theoretically, people claim that this kind of moire structure within this tungsten telluride or molybdite telluride can induce the heavy-fermion-like behavior. So that's my answer. So within just monorail limit, yeah, I do not think it can exhibit the heavy-fermion behavior because there is no local magnetic moment. So we need extra thing to get heavy-fermion physics. And the third question is that I'm curious, is there any way we can probe directly Kondo crowd or Kondo screening? So experimentally, the most, I think, so to confirm the heavy-fermion physics, I think usually we can track the resistivity and heat capacity, something like that. So if the resistivity shows some maximum behavior, then we can say that, the Kondo singlet can participate the Fermi surface formation, and then it makes some coherence. So if you can find some resistivity maximum behavior, then we can define the resistivity maximum point as a coherence temperature, and we can claim that there is some kind of heavy-fermion behavior. But in addition, we also need some kind of heat capacity measurement. So if the F electron participate into the Fermi surface, usually the Zomack coefficient is become very large compared to the normal metallic system. So by combining these two measurements, usually people claim that we have some heavy-fermion behavior or not. And by using the RPS, although it is quite difficult because the energy scale of the F electron is too tiny, but actually the direct measurement is the RPS measurement. By changing the temperature, we can follow the evolution of the electronic structure. That's the direct observation. But because of the temperature scale, it is not easy. And finally, I think we can also track the optical conductivity measurement. So because by lowering the temperature, if the F electron can participate the band formation, then the derivative peak will be sharp, and also the derivative peak can be stronger as we lower the temperature. And because of the hybridization between the conduction and F electron, it can induce the hybridization gap feature, and that kind of hybridization gap feature induce some new optical transition. So this kind of thing can be observed in the optical conductivity measurement. So that's my answer for the third question. And so is there the fourth question is there a difference in the cerium balance state between bulk and 2D cerium silicon iodine? I don't think so. So actually, local environment of the cerium atom in the cerium silicon material is same regardless of the exfoliation. So the cerium atom just remain, the balance of cerium atom remains same. So it exhibits the cerium 3+ case. So the F electron, it has one electron in the F shell. So the balance state does not change. And I think that's it from the chat.
Cool. That is fine. Okay. Is there anybody else want to ask? If not, then I have 2 questions. First one is like about the strange metal behavior when you approach the quantum critical point. is it only like found? Okay, I know that I saw like in the ytterbium, for example, ytterbium-based compound, you have this like strange metal behavior. But is it commonly found all only in the case of like heavy-fermion system, or is it like some people said I'm not I'm actually like following this kind of like topic, but as far as I know, like some people try to relate it, I mean, this strange metal to the Kondo flux breakdown or something, if I'm not mistaken. And maybe you can comment on that. And the second one is like about, yeah, I mean, still like the previous question about the valence. Actually, like cerium can be, as you know, like cerium can be 3+ or 4+.
Yeah, yeah.
And also it can be also in the intermediate valence state. And as we know, like when you apply like strain or pressure in your case, like you do like you did like compressive strain in the case of the cerium silicon iodide, then like as we know, like if you tip the valence between, I mean, into the mixed valence state, then what you can, I mean, like what you will expect. And also, like I have like I'm still like curious. I asked this question like long time ago to my colleague in the US, and then like, but he didn't answer. He just like, I mean, like it's about like quantum critical point. Do you think like there's some kind, I mean, quantum critical point induced by pressure? Do you think this kind of like QCP can be related also to this valence transition or not?
So, okay,
So those are two questions.
okay. So first question is, so I mean, it's for the first question. So actually, this kind of quantum critical point actually can be found in, yeah, non-lanthanide or non-heavy-fermion systems. So actually, even for the some cuprate system, I mean the copper-based superconductor or the ion-based superconductor, actually there can be some competition between the spin density wave or the magnetic ordering between the subparamagnetic phase. So actually, this kind of quantum critical point can be found many strong correlated systems, including the cuprate and this kind of heavy-fermion system. So actually, there are some very common feature between the cuprate superconductor and the heavy-fermion superconductor. Although the origin of them is controversial, but still they share many common features near this kind of quantum critical point. So is it enough for the first question? So I forgot the detail of the first one.
Yes, yes.
Yeah. So for the second question, so what else? The second question, mixed balance and
Yeah, but like mixed balance, and then especially in this case, like when you, yeah, first is about like when you apply strain, and we should consider like possibility of you have to induce also
okay.
like to mixed
So
balance state, and what
so
will happen,
in
and
the
also, I mean, with the whether like QCP commonly found, is it also related to?
So okay, so the first one is that actually in this calculation I did not consider any some balance state change. So I think within this kind of this external perturbation, I mean the compressive strain or the surface doping case, actually we did not find any evidence for the balance state change. So actually in this study we did not consider the balance state change. However, and actually balance state change can also induce the quantum critical point, as you already mentioned. So I forgot the exact compound, but I think the silicon copper to silicon 2 case, actually, yeah, people suggest that by applying the pressure, they are actually in the silicon copper to silicon 2 compound, people found two different superconducting dome under the pressure. So people claim that the second superconductivity dome is connected to the quantum critical transition based on the balance state change. So I think, yeah, it is possible to obtain some quantum critical point and even the superconductivity under the pressure by tuning the balance state change. And finally, so for the mixed balance heavy-fermion, so actually recently the people actually are interested in the mixed balance heavy-fermion system, but it can be misleading because actually the mixed balance material, actually that means there is some kind of charge fluctuation between two different the balance state. But actually, the charge fluctuation energy scale is much larger than the Kondo energy scale. So if there is some charge fluctuation, it can easily screen the magnetic moment. So usually the mixed balance heavy-fermion system usually have much larger Kondo energy scale. But actually, I do not want to say it is Kondo energy scale. So it can be misused, but anyway, so if you just consider the screening from the balance fluctuation is also some screening behavior, then mixed balance material usually exhibit larger Kondo energy scale. So recently I'm working on the mixed balance heavy-fermion system, and then that kind of material exhibit more than the Kondo temperature scale of that kind of mixed balance material is more than 200 Kelvin or 300 Kelvin, which is much larger than this kind of typical heavy-fermion system, cerium cobalt indium 5. So I think mixed balance can even give larger energy scale. So maybe it is
So okay,
it can
so
be
let
more
me clarify.
interesting.
So if the Kondo scale, usually it's very low temperature, like maybe like I don't know, 2 Kelvin, 5 Kelvin, something like this.
But
So if you have like mixed balance, then you can like push the Kondo like scale. Like do you think like what's temperature like? I mean, like, is it like 100 Kelvin still like
so
acceptable?
actually the proper definition of the Kondo temperature scale is also controversial. That's the first point. So even these days, so actually when I was in Los Alamos, actually the people, they do not have any the good definition for the Kondo energy scale. But based on my energy scale, my definition, actually this kind of the cerium cobalt indium 5 or cerium rhodium indium 5, the Kondo energy scale is around, I don't know, 115 Kelvin, something like that. So actually I do not want to say about the Kondo energy scale. I just want to say about the coherence energy scale, which can be defined from the resistivity maximum. That is more clear definition. So I just explain it within the Kondo coherence energy scale. So for the cerium cobalt indium 5 and cerium rhodium indium 5, the coherence energy scale, temperature scale is about 15 Kelvin. But recently, the mixed balance material, the coherence energy scale is more than 100 Kelvin. So the energy scale, temperature scale, and energy scale is much larger than the typical just cerium 3+ based heavy-fermion system.
Okay, I understand. But do you think like this is also this is only limited for cerium, or we can also get this kind of like this kind of like shift in the coherence temperature in the ytterbium case?
You can get same physics in the ytterbium case, and actually for the ytterbium case there are many mixed balance case compared to the cerium case. So mixed balance usually, I think, more important in the ytterbium case compared to the cerium case. Although we have some mixed balance system in the cerium based material, but in my as far as I know, there are many mixed balance system in the ytterbium side.
I see. Okay, so we have one more question. Maybe you can read it directly. Ooh, this guy.
That's a good question. So nowadays, people are crazy about the arthomagnetism. So actually, these days I'm studying the arthomagnetism, and this can be also a good topic, but still I do not have the good answer for this one, because to get an intrinsic heavy-fermion system, we have to find the electron based arthomagnetic system, and we need to analyze the symmetry to confirm whether it is arthomagnetism or not within the lanthanide or akinine system. But I don't think there is such kind of study, and I don't have any candidate for that. But I believe that if we can get you can get some cerium-based material with the proper symmetry, then why not? We can get a heavy-fermion behavior with the ultramagnetism. But another point is that even the definition for the ultramagnetism is not clear. So from the first paper from the Smith lab, the ultramagnetism is defined within the without the spin-orbit coupling. I mean, without the non-collinear spin. But actually, for the lanthanide material, we have very strong spin-orbit coupling, and we cannot consider that kind of situation. So definition is not that clear in our system. But these days, people are trying to make some another definition for the ultramagnetism, and people actually are studying some ultramagnetism in the very heavy atom case. So I think we can realize the both physics in some cerium or ytterbium or lanthanide material, but still I do not have any candidate for that. But I think it is possible.
This one is interesting because because maybe not in the metallic, because some people look now these days like into the oxide system that which can host the ultramagnetism as well. So it could be interesting. So okay, if there's no question, and then we are approaching the end. So in the end, I think like we can finish. Thank you for the audience, and thank you for Dr. Gyu Jang for your talk presentation, and then I really appreciate that your willingness to give a talk in our institute. So hopefully that we can you can come to visit us next time in the future, and maybe we can do like some kind of like research collaboration also in the near future with you and with our colleagues in our institute. So with that, again, and I would like to thank all the audience and you especially. So we can finish this session. Thank you very much.
Okay. Thank you.
Bye.
Thank you.